Oh, okay. So I am Nagi Mekhiel, professor at Ryerson University. It's in Toronto. My research area in memory design. And so today I'm going to present just a new idea, a concept of no instruction computing, just using pointers and operations in registers to make the architecture more adaptable. So the motivation for this concept is we notice that the current architecture depends on delivering maximum number of instructions per clock cycles, which makes it more dependent on memory bandwidth. And still, memory bandwidth is an issue for high performance computing. So we also notice that for each fetch, the program counter only points to one instruction in the memory. And also, if you want to issue parallel instructions, you need to use either superscalar, VLIW, or multi-core, multiprocessors that you have to add the overhead of synchronization. So those are issues with conventional current architectures. And we also notice that the load store of data architecture helps to reduce memory traffic and makes the architecture less dependent on the memory for the data. So that was the motivation for this concept, which is no instruction computing, replacing the basically program counter with a register pointer that points to multiple operation on registers as well. So we use a load to transfer a block of code which consists of multiple operations and operands to the register file, sharing a register file with operations and also a pointer that points to those operations rather than using a single program counter that only points to one instruction at a time in the memory. So we have a single operation register pointer that consists of multiple pointers because it points to a register, then we can fit in one register multiple pointers to operations in a second level registers or lower level registers. The last field of that operation pointer register points to the next, to a register that has a pointer to the next code to be loaded to the register file. So it is a block of code that consists of that operation register pointer has multiple pointers to those operation registers that consist of multiple operations in registers rather than having an instruction register and one program counter. You need to increment and point to one location in memory. So also the operation pointer register, if it has one bit for the mode, it could easily switch from a sequential execution of those operations to a parallel operation if the mode is set as parallel in one cycle using multiple function unit in the architecture. So the organization of the concept is basically the top is a register pointer that points to either instruction cache or operation cache and the memory, and it points to the start address of a block of code that to be loaded to the registers. And the first one is the operation pointer register, and this consists of multiple of pointers. Each pointer points to an operation in a lower level registers like those registers here. And the last pointer points to the next, it points to a register, and the register points to the next block to be loaded to the register to execute the next code segment. So an example for an application is just adding an array of A of I to a constant and storing it back to array of A. So you notice this is the operation register pointer, and it has multiple pointers to those operation registers. The first register is a load, loading A of I to a register. Then the next pointer points to R2, which adds it to B. And then the third pointer is the store, storing it to the A of I location, and then incrementing I. And this is a branch compared to whether the loop limit has been still iteration n or not. If not, then it goes back to R1 to continue the loop. When it exits, this is another pointer that points to the next code that to be loaded for the next code segment to be executed. So all of this fits into like 6 registers and could be executed within the processor itself. No need to go to the memory except for a load and store. So to evaluate the performance, we put 1 cycle accessing registers. However, we added 2 cycles for a memory access. So an overhead of 2 cycles for accessing here, whether cache or memory, average 2 cycles. Then we look at the conventional architecture that uses an instruction register and the program counter, and calculate the time, that total time in cycles to execute n iterations of this loop. Executing each instruction in registers, it's 5n times 1 cycle, but plus we are going to load and store 2 access, 1 load, 1 store times each cycle, 2 cycles, 2n times 2 plus 5n, 5 instruction. Each instruction is 2 cycles to fetch it from the memory. So the total number of cycles came to about 19n cycles. That's the time to execute this loop in conventional architecture. The memory bandwidth is calculated by how much memory is used, divided by the number of cycles. So we have a load and store is 2n, and we have 5 instructions, 5 times n, 5n, each one is 4 byte or 1 word, divided by the number of cycles, 19n. It came up to be 1.5 byte per cycle. That's the bandwidth requirement for conventional architecture. When we evaluate the performance of no instructions computing, we find out that the total to execute 5 instructions is 5n times 1 cycles, and the overhead of just loading 6 of those registers only once, times each one 2 cycles, about 12 cycles, plus we have a load and store that's 2n, each one is 2 cycles. It came up to number of cycle 9n plus 12 cycles. So if n is 1000, almost this 12 is could be neglected. So we find out that the bandwidth, memory bandwidth requirement is only needed to load and store, which is 2n. Each one is 4 byte, divided by the number of cycles, which is 9n plus 12, about 0.89 byte per cycle. So what is the gain here of using this new concept is basically the performance gain is 19n, that's the number of cycles for conventional, divided by 9n plus 12 is about 202 times reduction in time. The bandwidth, memory bandwidth reduction is 1.5 byte per second divided by 0.89 byte per second is about 168% reduction in the requirement for memory bandwidths. So in conclusion, oops. So in conclusion, we conclude that with the no instruction computing, we get rid of the use of program counter that points only to one instruction in memory at a time. And also the new concept reduce the memory bandwidth requirement. Also, it improves the performance. The important part of it, using the pointers in one register pointer, is easy to support parallel operation. Parallel just by having one bit set to parallel. Also, it could support SIMD style, in which all instructions on the lower level registers have the same instruction accessing or processing different data streams. So this future work for this is to implement it, hopefully using FPGA, and develop some software tool to find the real performance advantage for this new idea. I published before using pointers in instructions, and also a long time ago I published just a simple article to say that no instructions was not good for slow memory, and that was published in EE Times 1999. So that just to point out to that the memory is a problem, and having instruction, fetching instruction every clock cycle of multiple of them is an issue, and said, okay, we should have a different concept. So with that, I conclude my talk, and if please you have any questions, I am going to put my email, because very soon I have to start a lecture, and but I really appreciate if you can send me any questions or to exchange ideas, and need some feedback from you to think of different approach, or also discuss anything. But I thank you for inviting me to this talk, and again, hopefully I can hear from you for questions or anything. I'll be happy to answer.